Hello, everyone, and a very warm welcome to today's presentation. I'm excited to share with you some insights on the CPU scheduling process. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. Today, we'll explore the fundamental concepts behind CPU scheduling, how it works, and why it is so crucial in operating systems. So, let's get started and dive into this interesting topic. Welcome to our discussion on CPU scheduling. So, what exactly is CPU scheduling? Well, it's the process that decides which process gets to use the CPU next. This is crucial because the CPU is a limited resource, and we want to make sure it's used as efficiently as possible. The main goals of CPU scheduling are to maximize CPU utilization, which means keeping the CPU busy as much as possible, ensure fairness so that no process is left waiting too long, and minimize waiting time for each process. These factors help improve overall system performance and user experience. In systems that support multiprogramming, multiple processes are loaded into memory at the same time. The scheduler's job then becomes deciding the order in which these processes will take turns executing. This decision-making process is what keeps everything running smoothly and efficiently. By understanding how CPU scheduling works, we can better appreciate how operating systems manage resources to deliver optimal performance. Let's take a closer look at the different types of CPU schedulers. First, we have the long-term scheduler, also known as the job scheduler. Its main role is to admit jobs into the ready queue, controlling how many processes are brought into the system at any given time. This helps balance the workload and ensures the system isn't overwhelmed. Next, there's the short-term scheduler, sometimes called the CPU scheduler. This one is responsible for selecting which process from the ready queue will run next on the CPU. It's all about making quick decisions to keep the CPU busy and maximize efficiency. Finally, we have the medium-term scheduler. Its job is a bit different. It manages the swapping of processes, suspending and resuming them as needed. This helps in managing memory and system responsiveness, especially when the system is under heavy load. Understanding these schedulers is key to grasping how the operating system efficiently manages multiple processes and maintains smooth performance throughout the system. Let's take a closer look at CPU scheduling criteria, which are essential for evaluating how well a scheduling algorithm performs. First, we have CPU utilization, which aims to keep the CPU as busy as possible, minimizing idle time and ensuring efficient use of resources. Next is throughput, the number of processes completed per unit time. Higher throughput means the system is processing more jobs in less time. Then there's turnaround time, or TAT, which measures the total time from when a process is submitted until it's completed. This is a key indicator of overall system responsiveness. Following that is waiting time, or WT, which is the amount of time a process spends waiting in the ready queue before execution begins. Minimizing waiting time helps improve system responsiveness. Finally, response time is the interval from process submission until the first response is produced, which is critical for interactive systems where quick feedback is expected. Now, to clarify how we calculate some of these metrics, the turnaround time is equal to the completion time minus the arrival time, and waiting time is the turnaround time minus the burst time. Understanding these criteria helps us evaluate and improve the efficiency of CPU scheduling algorithms, ensuring better performance and user experience across the system. Now let's talk about the first-come, first-served scheduling method, or FCFS for short. In this approach, processes are executed strictly in the order they arrive. So the process that arrives first gets executed first, then the next, and so on. It's a non-preemptive algorithm, which means once a process starts executing, it runs until it finishes. It doesn't get interrupted by other processes. To make this clearer, consider this example. We have three processes, P1, P2, and P3. P1 arrives at time 0 and needs 4 units of time to complete. P2 arrives at time 1 with a 3-unit burst, and P3 arrives at time 2 with just a 1-unit burst. When we look at the Gantt chart, it shows P1 running first, then P2, then P3. From this, we can compute the average waiting time, which turns out to be approximately 2.67 units, and the average turnaround time, about 6.33 units. These are important metrics because they help us understand how long processes are waiting and overall system efficiency. One of the main advantages of FCFS is its simplicity. It's straightforward to implement because it follows a basic first-in, first-out logic. However, there are some drawbacks. For example, it can cause what's called the convoy effect, where a long process can delay all the processes that follow, leading to inefficiency and increased waiting times. Understanding these strengths and weaknesses helps us see how FCFS fits into the broader picture of scheduling strategies, especially when balancing simplicity against potential delays. Now let's talk about shortest job first, or SJF scheduling. Essentially, this approach means that the process with the smallest burst time gets executed first. It's a straightforward idea, but it can be implemented in two ways: preemptively, which is known as shortest remaining time first, or SRTF, or non-preemptively. The goal here is to minimize the average waiting time for processes, making it optimal in that regard. The main advantage of SJF is that it significantly reduces the average waiting time, which improves overall system efficiency. However, there's a catch. This method requires prior knowledge of each process's burst time. That means you need to know how long each process will take beforehand, which isn't always practical. So, in the context of our overall discussion on scheduling algorithms, SJF's effectiveness in minimizing wait times is clear, but its reliance on prior knowledge is a key limitation to keep in mind. Let's take a look at this example of the shortest remaining time first, or SRTF, scheduling algorithm. We have 4 processes here: P1 with a burst time of 8, P2 with 4, P3 with 2, and P4 with just 1. Now, the key idea with SRTF is that at any given moment, we select the process with the shortest remaining time to execute next. In this example, the execution order goes like this: P4 first, because it has the shortest burst time of 1. Then P3, which has 2 units remaining, follows. After that, P2 with 4 units, and finally P1, which takes the longest at 8 units. This order ensures that we're always working on the process closest to completion, minimizing waiting time. Speaking of which, the average waiting time here is approximately 4.75 units. That means, on average, processes spend about this much time waiting before they get executed. Additionally, the average turnaround time, which includes both waiting and execution, is roughly 8.25 units. These figures highlight how SRTF can improve responsiveness and reduce overall waiting time compared to other scheduling methods. When we connect this to the broader theme of process scheduling, it's clear that choosing the right algorithm can significantly impact system performance and efficiency. Let's talk about round-robin scheduling now. In this approach, each process is given a fixed time quantum, which is basically a small slice of CPU time. The idea is to give every process a fair chance to run, ensuring that no process gets stuck waiting too long. It's considered a preemptive algorithm, meaning the CPU can interrupt a process when its time quantum expires and switch to the next process. This helps maintain fairness across all processes. For example, imagine we set the time quantum to 4 units. We have 4 processes: P1 with 8 units, P2 with 4, P3 with 9, and P4 with 5. The execution order would be P1, then P2, then P3, then P4, and back to P1, and so on, cycling through them until all are complete. One big advantage of this method is that it promotes fair allocation of CPU time, making it especially useful in time-sharing systems where many users need quick access. However, there's a trade-off. If the quantum is too small, the system will spend a lot of time switching between processes, which we call context switching. This can introduce overhead and reduce overall efficiency. So, choosing the right quantum size is a key factor in optimizing round-robin performance. Now, let's talk about priority scheduling. In this approach, each process is assigned a priority value, which helps determine the order in which processes are executed. The CPU is given to the process with the highest priority at any given time. This method can be either preemptive, meaning a higher priority process can interrupt a running process, or non-preemptive, where a running process isn't interrupted until it finishes. One of the main advantages of priority scheduling is that it's especially suitable for real-time systems, where certain tasks need to be completed promptly. However, there is a downside we need to be aware of: starvation. That's when lower priority processes wait indefinitely because higher priority processes keep coming in. To tackle this, we use a technique called aging, which gradually increases the priority of waiting processes over time, ensuring fairness. So, in the context of our overall discussion, priority scheduling offers an effective way to manage process execution based on importance, but it requires careful handling to avoid issues like starvation. Let's take a closer look at multi-level queue scheduling. In this approach, processes are divided into different queues based on their type. For example, we have system processes, which are critical to the operating system, interactive processes that require user interaction, and batch processes that run in the background without user intervention. Each of these queues has its own specific scheduling algorithm tailored to the nature of the processes it contains. This way, we can optimize the way each type of process is handled. Now, there's a fixed priority between these queues, meaning that higher priority queues, like system processes, get preference over the others. One of the main advantages of this method is efficient classification of processes. By categorizing them, the system can manage resources more effectively. However, there's a downside to be aware of. Lower queues might suffer from starvation. That is, processes in the lower priority queues could end up waiting indefinitely if higher priority processes keep arriving. This overall approach fits into our broader discussion of scheduling techniques by showing how we can balance efficiency and fairness in process management. Now, let's take a closer look at multi-level feedback queue scheduling. Essentially, this approach allows processes to move between different queues based on their behavior. So, if a process uses up its allotted time without finishing, it might be moved to a lower priority queue. Conversely, if a process is new, it typically starts in the highest priority queue to give it a better chance to run quickly. This dynamic movement helps manage processes more fairly and efficiently. Two key techniques used here are aging and feedback. Aging gradually increases the priority of waiting processes, which helps prevent starvation, where some processes might otherwise wait indefinitely. Feedback, on the other hand, adjusts priorities based on how processes behave during execution. One major advantage of this system is its flexibility and efficiency. It adapts to different process behaviors, ensuring a more balanced and responsive scheduling. However, this flexibility comes with a trade-off. The implementation can be quite complex. Managing multiple queues and priority adjustments requires careful design and handling. Overall, multi-level feedback queues are a powerful method to optimize process scheduling, balancing fairness and efficiency, even if they do require more sophisticated implementation. Now, let's take a look at a comparison of different CPU scheduling algorithms, starting with first come, first served, or FCFS. This one is non-preemptive, meaning once a process starts executing, it can't be interrupted. As a result, it doesn't offer preemption, and its fairness level tends to be low because longer processes can cause delays for shorter ones. Moving on to shortest job first, or SJF. This algorithm can be both preemptive and non-preemptive, depending on the implementation. Its goal is to reduce average waiting time by prioritizing shorter processes. Fairness here is medium. It's better than FCFS, but can still lead to some issues if short processes keep arriving. Next, we have round robin, or RR. This is a preemptive algorithm, which means it allows processes to be interrupted after a fixed time quantum. Because of this, it offers high fairness, giving each process a fair share of CPU time, making it suitable for time-sharing systems. Then there's priority scheduling, which can be both preemptive and non-preemptive. This algorithm assigns priorities to processes, but fairness can vary. Sometimes it's high, sometimes low, depending on how priorities are managed. It can be unfair if high-priority processes monopolize CPU time. Next, multi-level queue scheduling can also be both preemptive and non-preemptive, with processes assigned to different queues based on their priority or type. Fairness varies, but it generally offers medium fairness, as processes are grouped and scheduled within their queues. Finally, we have MLFQ, or multi-level feedback queue. This is a preemptive algorithm that dynamically adjusts process priorities based on their behavior. It provides high fairness by allowing processes to move between queues, preventing starvation, and ensuring that all processes get CPU time fairly. In summary, these algorithms vary in terms of preemption and fairness, and understanding these distinctions helps us choose the right one based on system needs and workload characteristics. All right, let's walk through this example of calculating WT and TAT step by step. We have a set of processes, each with their own arrival times and burst times. For instance, process 1 arrives at time 0 and needs 5 units of time to complete. Process 2 arrives at time 1, requiring 3 units, and so on. Now, the key formulas here are quite straightforward. Turnaround time, or TAT, is simply the completion time minus the arrival time. This tells us how long a process has been in the system from start to finish. Waiting time, or WT, on the other hand, is the turnaround time minus the burst time. Essentially, it measures how much time the process spent waiting in the ready queue, not actively using the CPU. In this example, using the first-come first-serve scheduling, the completion times are calculated as follows. P1 finishes at time 0 plus 5, P2 finishes at 4, P3 at 7, and P4 at 15. From these, we can determine the average WT and TAT. For WT, it sums up to about 6.5, and for TAT, around 12. The main takeaway here is understanding how these calculations reflect the efficiency of our scheduling algorithm and help us evaluate process performance. So always remember, calculating WT and TAT gives us crucial insights into process management and overall system responsiveness. Now, let's look at the difference between preemptive and non-preemptive scheduling. In preemptive scheduling, the CPU can actually be taken away from a process before it finishes. This is particularly useful in time-sharing systems, where we want to ensure that all processes get a fair share of CPU time. Examples of preemptive algorithms include round, robin, and shortest remaining time first, which actively manage the CPU to improve responsiveness. On the other hand, non-preemptive scheduling means that once a process has the CPU, it keeps it until it completes. The CPU isn't taken away mid-process. So, in this case, processes run to completion once they start, unless they voluntarily release the CPU. Examples here include first come, first served, and shortest job first, which are simpler but can lead to longer wait times for some processes. Understanding this distinction is essential because it influences the system's responsiveness and throughput. Preemptive scheduling tends to be more flexible and responsive, while non-preemptive scheduling is simpler but can cause delays. Connecting this to our overall theme, choosing between these methods depends on the specific needs of the system, whether we prioritize fairness, responsiveness, or simplicity. Now, let's look at some key advantages of CPU scheduling. First, it allows for efficient utilization of the CPU, which means we make the most out of the processing power available. When scheduling is done effectively, it helps prevent the CPU from sitting idle, waiting for tasks, and keeps it busy with meaningful work. Next, we see an increase in throughput. This basically means that more processes are completed in a given amount of time, boosting the system's overall productivity. It's a vital factor for system performance, especially in environments with many processes running simultaneously. Another important benefit is the reduction in waiting and turnaround time. By scheduling processes wisely, we minimize the time processes spend waiting in the queue and improve how quickly they complete, which leads to a more responsive system. This directly impacts user experience because tasks finish faster. Additionally, CPU scheduling ensures fair allocation among processes. It's crucial that no single process hogs the CPU, which promotes fairness and prevents starvation. Every process gets a chance to run, maintaining system stability and fairness. Finally, effective scheduling significantly improves system responsiveness. Whether it's a user interacting with an application or a real-time process, scheduling helps keep the system reactive and smooth, ensuring that users feel the system is quick and reliable. All these advantages tie back to our goal of creating efficient, fair, and responsive computing environments. Now, let's take a look at some of the limitations and disadvantages associated with these scheduling algorithms. First, some algorithms can cause starvation, which means certain processes may end up waiting indefinitely if higher priority tasks keep getting scheduled. This can be a real issue in ensuring fairness across all processes. Next, preemptive scheduling, while useful for responsiveness, increases the overhead due to frequent context switching. Every time the CPU switches from one process to another, it incurs some cost, and too many switches can degrade overall performance. Another challenge is accurately predicting burst times, the amount of CPU time a process needs. Since these times are often unpredictable, making precise scheduling decisions becomes quite difficult, potentially leading to suboptimal performance. Finally, more complex algorithms like multi-level feedback queues, or MLFQ, are powerful but hard to implement efficiently. Their complexity can make them difficult to tune and maintain, especially in real-world systems where simplicity and reliability are key. Overall, while these algorithms are designed to improve process management, understanding their limitations helps us choose and optimize them effectively in practical scenarios. Let's wrap up with a quick summary of CPU scheduling. As we've seen, CPU scheduling is absolutely vital for effective process management. It helps ensure that processes are given access to the CPU in a way that keeps everything running smoothly. Each scheduling algorithm has its own set of trade-offs, especially when it comes to fairness versus efficiency. For example, some algorithms prioritize fairness, making sure every process gets a turn, while others focus on maximizing overall system throughput. Specifically, shortest job first, or SJF, is great for minimizing waiting time because it always selects the process with the shortest burst time next. But of course, this requires knowing the burst times in advance, which isn't always practical. On the other hand, algorithms like round-robin and multi-level feedback queue are ideal for time-sharing systems. They distribute CPU time fairly among processes, making sure no single process hogs the CPU, which is key for interactive environments. So, understanding these differences helps us choose the right scheduling approach based on the system's goals, whether that's fairness, efficiency, or responsiveness. So, to wrap things up, CPU scheduling is all about optimizing the order in which processes are executed to improve overall CPU performance. By carefully choosing the right scheduling algorithm, we can ensure that system resources are used efficiently and processes are handled smoothly. Now, the choice of the specific scheduling algorithm really depends on the type of system we're dealing with, whether it's a batch system, a real-time system, or an interactive one. Each has its own unique requirements and priorities, so the algorithm must be suited accordingly. Finally, understanding key metrics like waiting time and turnaround time is crucial. These help us analyze how efficient our scheduling is and identify areas where we can improve. All these points tie back to the overall goal of making our systems faster, more responsive, and more efficient. Thanks for following along through this presentation.